Okay, for another example, we have 460 volt terminal face-to-face voltage. The output rated power value is 25 horsepower and the applied voltage frequency is 60. We have 4-pole machine. The machine input terminals are connected in Y and equivalent circuit parameters are given R1, X1, R2, X2, and XM, but we don't have RC. So, because of this, during the analysis, we can use the simplified equivalent circuit without RC. But RC effect, the core losses effect, is combined with the rotational losses. So, rotational, that means friction, windage, stray, and additionally core losses are totally 1100 watts. And the sleep value is also given, which is 2.2%. So let's calculate some parameters. We can start with the speeds of the system. Which speeds we have? Basically, we have two speeds, synchronous speeds and the motor speed. And we have two different units of this speeds. So because of this, we will calculate 4 different values in terms of speeds. And we can start with an S calculation with 120 F over P. So 120 times the given frequency of 60 divided by the number of poles, which is 4, will give us 1800 RPM. And similarly, Nm, the motor speed, can be calculated with 1 minus S and S. 1 minus the sleep value, which is 0.022, times our calculated synchronous speed will be 1760 RPM. What else? The speeds are calculated in revolution per minute unit. We can calculate their radian per second versions for the torque power calculations. So for this, we have Ws and Wm, the synchronous speed and the motor speed in radian per second. For this calculation, the speed values must be multiplied by 2 pi over 60. 2 pi radian is equal to 1 revolution, and we divide it to 60 because of the minute to second conversion. And similarly, for the last one, it will be 2 pi over 60 times Nm. And from here, we can calculate the first one as 1088.5 radian per second. And the last one, Wm, the motor speed in radian per second, can be calculated as 184.4 radian per second. Okay, so in the next part, we can calculate the input current of the induction motor. So to calculate the input current, we need to examine the circuit and we have to calculate the total impedance of the induction motor. So for this case, if we use the simplified equivalent circuit, our circuit will look like this figure, and we have R1, X1, X2, R2 over S, and the XM. According to given values, R1 is equal to 0.641 ohms. The next one is 1.106 ohms, and XM 26.3 ohms, X2 0.464 ohms, and the last one R2 over S. It is not given directly, R2 value is given. So R2 is 0.332 ohms. We must divide to slip. So from here, it will be 15.09 ohms. Now we know the equivalent circuit parameters, and we can find the value of V1, which is the input voltage of this per phase equivalent circuit. So we can calculate what is the I1 value, magnitude, and the angle we can determine. So to be able to find I1, we should find the total impedance. So when we examine the circuit, we can start from the right part, and first of all we have a series connected two components. And if we look from here, and if we can say Z2 is defined as the impedance for the right side, Z2 will be R2 over S and JX2. And it will be 15.09 and 0.464. Or we can write also in polar form 15.10 with 1.76 degree will be the impedance of the right side. Then what we have? Then we have a parallel connection of XM with this Z2. And let's call it as ZM. For Zm, we have a parallel connection 1 over JXM and 1 over Z2. So if we write the values, 1 over 26.3 and 1 over 15.10 with 1.76. From here, we can find the result as 12.94 with 31.1 degree. This is the Zm, so right side parallel connection is calculated. Now, the lost resistance total equivalent impedance of the system can be calculated. How? But with the series connection of R1, XM, R1, X1 and Zm. For the next one, Z equivalent will be R1, X1 and Zm. According to given values, it will be 0.641, 1.106 and 12.94 with 31.1 degree. And from here, that equivalent can be calculated as 14.07 with 33.6 degree. And now it's possible to calculate the current value. I1, which is the input current of the circuit, will be the V1, the voltage, divided by total impedance. What is the voltage? If we check the given values, 460 is given. What was the 460? It is phase-to-phase terminal voltage. So 460 must be divided to square root 3 because the system is connected in Y, and in here we have to write the phase to neutral voltage. And if we divide to total impedance value, which is 14.07 with 33.6 degree, we can find 18.88 with minus 33.6 degree. This is the current of the input side. What else? The power factor also can be determined. Input power factor will be cosine 33.6. Because the voltage is our reference with 0 degree, So the angle between the voltage and the current will give us the power factor of the system. So 0.833 will be the power factor value, and because of the minus in here, we have to write the lagging with the value. Then we can continue with the power and the losses. And in the next part, for example, we can calculate the input power of the circuit. So the input power can be calculated with square root 3 terminal voltage, line current, and cosine theta. Or with the other version of the input power expression, we can write 3 times V phase, I phase, and cosine theta. For the first one, 460 is the terminal voltage of the circuit, and IL can be used directly for the terminal current also, because we have a Y-connected system. So 18.88 will be the current. And cosine theta, according to our calculation, will be 0.833. Or with the second version of the input power calculation, we can write V phase 460 divided by square root 3. Current will not change because phase and the line currents are equal to each other in Y connection. So 18.88, and same power factor will be here. So 12,530 watts will be the input power of this induction motor. The next calculation can be the stator copper losses. We know the current, we know the resistance value, so stator copper losses can be calculated with 3 times the current flowing through the stator winding resistance square times the stator winding resistance value. So 3 times 18.88 square, 0.641, which is the resistance value, will be 685 watts. The next calculation can be the air gap power. For the air gap power calculation, if we follow the power flow diagram, it should be input power minus stator copper losses, and also we must continue with the core losses in this expression. But core losses is combined with the rotational losses. In the equivalent circuit, we changed its order. We transferred it, we lumped with the rotational losses. Because of this, in here, we cannot subtract it. So the expression must be input minus stator copper losses. But if we continue as generic version of the equivalent circuit, also core losses must be used in this expression. 12,530 watts minus 685 watts of stator copper losses will be 11,845 watts. This is the power transferred to the rotor part. Then let's continue with the converted power. P converted will be air gap minus rotor copper losses. So for the rotor copper losses, we can calculate through the similar calculation with stator copper losses, but we don't know the current flowing through the right side, rotor side. So instead of additional calculation, let's use the relation between the air gap power and the converted power. 1 minus S air gap power will be the converted. So 1 minus 0.022 times air gap power, which is 11,845, will be 11,585 watts. And for the output power of the system, from here we can continue with the rotational losses. Output power will be converted minus rotational losses, and 11,585 minus 1,100 watts, which includes the friction, windage, stray, and for this example also it includes the core losses. So 10,485 watts will be the output power according to our operation point. And when you convert to horsepower, which will be equal to 14.1 horsepower, and according to our rated value, which is 25 horsepower, 100% rated output power of the system, we have less power. So it will be nearly 56% rated system we have. What else? The torques can be calculated. For example, the induced torque, which is the related with the converted power. So converted power over Wm can be used for induced power calculation. Or let's use another relation between the parameters. Instead of converted power, we can write 1 minus S air gap power over, for Wm also we have a similar relation with the synchronous speed. So 1 minus S Ws can be also written. So with the air gap and the Ws ratio, or converted power with Wm ratio can be used to calculate the induced torque inside the induction motor. So let's use the air gap version. So 11,845 watts will be divided to 188.5 radian per second. So from here, 62.8 Newton meter will be the induced torque of this machine. Similarly, the load torque, output torque, shaft torque of the machine can be calculated with the output power and the Wm. According to our calculations, output power is 10,485 watts, and the Wm, which is the motor speed in radian per second, is equal to 184.4 radian per second. So 56.9 Newton meter will be can be used at the shaft. And related to the system, the last calculation can be the efficiency. Output power divided by input power can be calculated. So the output power is 10,485 watts and the input power is 12,530 watts. So from here we can calculate the efficiency as 83.7%. Thank you for watching.